Far out in the darkness of our solar system, suspended in the gentle void between worlds, there exists a planet of remarkable quietness. Saturn drifts in its orbit nearly 900 million miles from the Sun, a distance so vast that sunlight takes 80 minutes to reach its cloud tops. At that distance, the Sun appears smaller in Saturn's sky, a distant point of light that still governs the planet's long, slow seasons. Saturn moves through space at a speed of 21,637 miles per hour, but from our perspective on Earth, this motion seems almost serene, a patient journey through the outer reaches of our cosmic neighborhood. This is a world that rewards slow observation. Unlike the dramatic turbulence of Jupiter or the subtle mysteries of distant Neptune, Saturn presents itself with a kind of understated grandeur. Its rings catch whatever light reaches them and scatter it across the surrounding space. Its atmosphere holds storms that have persisted for decades, following patterns we are only beginning to understand. Its family of moons includes worlds with subsurface oceans and organic chemistry unfolding beneath frozen crusts. What makes Saturn particularly suited for quiet contemplation is not just its beauty, but the timescales on which it operates. A single year on Saturn lasts 29.4 Earth years. The storms we observe have been circling the planet since before many of us were born. The rings, whether young or ancient, change so gradually that human observation captures only the smallest fraction of their evolution. In learning about Saturn, we encounter a pace of change that invites us to slow our own thinking, to consider processes that unfold across decades and centuries rather than moments. Tonight, we will explore this distant giant not with urgency, but with the patience it deserves. We will move through its characteristics one layer at a time, building an understanding of how this planet came to be, what it is made of, and what quiet wonders it holds. There is no need to rush. Saturn has been turning in its orbit for more than 4.5 billion years, and it will continue long after our brief observation has ended. Let the details settle over you gently. Some will be precise measurements, numbers that scientists have gathered through years of careful study. Others will be broader descriptions of processes that span millions of miles. All of them are invitations to imagine a world very different from our own, yet governed by the same physical laws that shape everything in the universe. As we begin, simply listen. Let the image of Saturn form gradually in your mind, a pale golden sphere surrounded by flat, bright rings turning slowly against the darkness of space. There is nothing you need to do but allow the information to arrive, fact by fact, creating a picture of one of the most fascinating objects ever studied by human beings. Saturn's story begins not with the planet as we see it today, but with the formation of our entire solar system approximately 4.6 billion years ago. In the region of space where our Sun and its family of worlds would eventually form, there existed a vast, slowly rotating cloud of gas and dust. This nebula, composed primarily of hydrogen and helium left over from earlier generations of stars, began to collapse under its own gravity. As it contracted, it spun faster, flattening into a disk with a dense concentration at its center that would become the Sun. Within this spinning disk, particles began to stick together through countless gentle collisions. Dust grains no larger than specks accumulated into pebbles. Pebbles clumped into boulders. Boulders aggregated into planetesimals, objects ranging from meters to kilometers across. This process continued, driven by gravity and the mechanics of orbital motion, for millions of years. The disk was not uniform. Closer to the forming Sun, where temperatures were higher, only materials with high melting points could remain solid. Farther out, beyond what astronomers call the frost line, water could freeze and volatile compounds could condense. Saturn formed in this outer region where ice was abundant. Current scientific understanding suggests that the giant planets, including Saturn, began as rocky and icy cores that grew large enough, perhaps 10 to 15 times the mass of Earth, to gravitationally capture the hydrogen and helium gas that filled the disk around them. Saturn's core likely reached this critical mass within the first 10 million years of the solar system's existence, making it one of the first planets to form. Once its gravity became strong enough, gas from the surrounding nebula began falling onto the growing planet, a process that continued until the disk's gas was either consumed by the growing giants or dispersed by the young sun's radiation. The Saturn that emerged from this process was considerably larger than it is today. Young gas giants are hot from the energy of their formation. The gravitational potential energy of all that infalling material converts to heat. Over billions of years, Saturn has been slowly cooling and contracting, radiating away that primordial warmth. Even now, Saturn emits about 2.5 times more energy than it receives from the Sun, a gentle glow from its deep interior that speaks to the heat still locked within the planet from its formation. Between 4 and 4.5 billion years ago, the architecture of the outer solar system underwent a dramatic rearrangement. The giant planets did not form in their current positions. Jupiter and Saturn likely started closer to each other, and possibly closer to the Sun than they are now. As they orbited, they interacted gravitationally with the remaining planetesimals and with each other. These interactions caused the planets to migrate, moving inward or outward depending on how they exchanged angular momentum, with the disk of material around them. Scientific models suggest that Saturn and Jupiter eventually fell into what is called a mean motion resonance, where Saturn completed one orbit for every 2 that Jupiter completed. This resonance amplified their gravitational interaction, pushing both planets outward and sending Uranus and Neptune tumbling into the distant reaches of the solar system. The migration scattered countless small bodies throughout the solar system, some crashing into the inner planets in what may have been a late heavy bombardment roughly 4 billion years ago. Others were ejected entirely, cast out into interstellar space by close encounters with the giants. Saturn settled into its current orbit about 4 billion years ago, circling the Sun at an average distance of 886 million miles, or 1.4 billion kilometers. In astronomical units, where 1 AU equals the distance between Earth and the Sun, Saturn orbits at 9.5 AU. This distance places it firmly in the outer solar system, in a region where sunlight is weak and temperatures are frigidly cold. The planet that stabilized into this orbit was already recognizable as the Saturn we know today, though likely without the rings it would later acquire. It had its thick atmosphere of hydrogen and helium. It had its deep interior layers where pressure transforms hydrogen into exotic states of matter. It had begun to accumulate its family of moons from a disk of material that orbited the young planet, much like a miniature version of the solar nebula that had formed the Sun and planets. These moons would play a crucial role in Saturn's later evolution. Some remained in stable orbits, others migrated inward or outward. Some may have collided and shattered, their fragments potentially forming the rings we see today, though the exact origin and age of Saturn's rings remains a subject of active scientific debate. What is certain is that by about 4 billion years ago, the basic structure of the Saturn system was in place. A massive gas giant attended by dozens of moons, all orbiting in a quiet region of the solar system where change happens slowly and where the Sun is a distant, diminished presence. From that point forward, Saturn has been cooling, contracting very gradually, and maintaining the basic character it established in those early epochs. The storms in its atmosphere have come and gone. Its moons have evolved through tidal interactions and internal processes. But the fundamental nature of the planet, a vast sphere of hydrogen and helium with a small core of rock and ice at its center, has remained unchanged for billions of years. When we observe Saturn today, we are seeing the product of processes that began when our solar system was young, when the Earth was still molten and lifeless, when the Sun was just beginning its long career of fusing hydrogen into helium. Saturn carries within it the memory of that distant time, encoded in its composition and structure. It is, in every sense, an ancient world, yet one that continues to be actively shaped by the physics of planetary interiors and atmospheric dynamics. Among all the planets in our solar system, Saturn holds a unique distinction that seems almost impossible when first encountered. This massive world, 95 times more massive than Earth, has an average density lower than water. The exact figure measured by scientists is 0.687 grams per cubic centimeter. Water, by comparison, has a density of 1 gram per cubic centimeter. This single fact tells us something fundamental about what Saturn is made of and how it is structured. If you could somehow construct a bathtub vast enough to hold Saturn, the planet would float. This thought experiment appears in many descriptions of Saturn, and while it is purely hypothetical, no such bathtub could exist, it captures something essential about the planet's nature. Saturn is not made of rock and metal like Earth. It is not even as densely packed as Jupiter, which has a density of 1.33 grams per cubic centimeter. Instead, Saturn consists almost entirely of the lightest elements in the universe, arranged in layers that become progressively denser toward the center. The outermost layer of Saturn, the part we can actually observe, is a vast atmosphere composed of approximately 96% molecular hydrogen and 3.25% helium by volume. These percentages come from careful analysis of sunlight reflected from Saturn's cloud tops and from measurements made by spacecraft that have visited the planet. The remaining less than 1% includes trace amounts of methane, ammonia, hydrogen deuteride, ethane, and other compounds. These minor constituents are what give Saturn its color and create the cloud features we observe. Hydrogen is the lightest element, and helium is the second lightest. Together, they make up about 98% of the observable universe's ordinary matter, so it should not be surprising that they dominate the composition of a planet that formed by gravitationally capturing gas from the solar nebula. What is remarkable is how much of Saturn is gaseous atmosphere and how much is material in stranger states. As we descend below the visible cloud tops, pressure increases. Pressure in an atmosphere comes from the weight of all the gas above pressing down. On Earth, atmospheric pressure at sea level is about 1 bar. On Saturn, as we move deeper, pressure climbs to tens of bars, then hundreds, then thousands. Under this mounting pressure, hydrogen begins to behave differently. It is no longer a gas but becomes a fluid, a liquid hydrogen ocean deep within the planet. Even deeper, where pressures reach millions of Earth atmospheres and temperatures exceed 10,000 degrees, hydrogen enters an even more exotic state. The molecules break apart, and the atoms are squeezed so tightly that their electrons can move freely between them. This creates what is called metallic hydrogen, a substance that can conduct electricity like a metal despite being composed of an element that under normal conditions is a gas. This layer of metallic hydrogen is thought to extend through much of Saturn's interior, surrounding a core of rock and ice. The core itself is small compared to the planet's overall size, perhaps 10 to 15 times the mass of Earth. But it is extraordinarily dense, compressed by the tremendous pressure of all the layers above it. The core likely contains iron, nickel, silicon, and various ices, water, methane, and ammonia that were frozen during the planet's formation and have remained solid, locked in place despite the heat and pressure, simply because there is nowhere for them to go. This layered structure, a solid core surrounded by metallic hydrogen, surrounded by liquid hydrogen, surrounded by an atmosphere that gradually transitions from liquid to gas, explains Saturn's low average density. The atmosphere is very light. The liquid and metallic hydrogen layers, while denser than the atmosphere, are still composed of the lightest element. Only the core has the kind of density we associate with rocky planets, and the core is a small fraction of Saturn's total volume. Saturn's radius, measured from its center to the top of its cloud layer at the equator, is approximately 60,300 kilometers, or 37,400 miles. This makes Saturn about 9 times wider than Earth. But because so much of that volume is occupied by lightweight hydrogen and helium, the planet's total mass is only 95 times Earth's mass. The same volume filled with rock and metal would produce a far more massive planet. This low density has other consequences. It means that Saturn has only a weak gravitational pull at its cloud tops compared to what a planet of its size might have if it were made of heavier materials. The surface gravity on Saturn, defined as the acceleration you would experience if you could somehow stand on top of its clouds, is only slightly greater than Earth's, about 9.0 meters per second squared compared to Earth's 9.8. A person who weighs 150 pounds on Earth would weigh about 160 pounds on Saturn, despite Saturn being so much more massive, because they would be standing thousands of kilometers above most of the planet's mass. Saturn's low density also means it is easily deformed by its own rotation. The planet spins rapidly, completing one rotation every 10.7 hours. This rapid spin creates a centrifugal effect that causes the equator to bulge outward and the poles to flatten. The difference is substantial. Saturn's equatorial radius is about 10% larger than its polar radius, making it the most oblate, the most flattened, of all the planets in the solar system. This bulge is visible in telescopic images, giving Saturn a slightly squashed appearance that adds to its distinctive character. The composition we observe today, that overwhelming dominance of hydrogen and helium, is not quite the same as what Saturn started with. The planet formed from the solar nebula, which had a composition very similar to the Sun, about 71% hydrogen and 28% helium by mass. Saturn's atmosphere shows a helium depletion compared to this primordial ratio. The current estimate is that Saturn's atmosphere is 18 to 25% helium by mass, somewhat less than expected. Scientists believe this depletion occurs because helium, being slightly denser than hydrogen, gradually separates out and sinks deeper into the planet over time. Deep inside Saturn, droplets of helium condense out of the metallic hydrogen and rain slowly down toward the core. This process, called helium differentiation, releases gravitational potential, energy as the helium falls, and this energy contributes to the excess heat that Saturn radiates. It is a slow process, occurring over billions of years, but it is one of the mechanisms that keeps Saturn's interior warm and drives some of the planet's atmospheric dynamics. Understanding Saturn's density and composition helps us understand not just this one planet, but the process of planet formation throughout the universe. Gas giants like Saturn are common around other stars. By studying Saturn in detail, its density, its atmospheric composition, its internal structure, we learn about how planets form from disks of gas and dust, how they evolve over time, and what kinds of worlds are possible in the universe. And there is something quietly astonishing about the fact that such a massive object, larger than 800 Earths in volume, can be so diffuse, so light, that it would float in an ocean. It reminds us that matter can exist in many states, that planets can be made of materials utterly unlike the rock and metal we stand on, and that the universe contains structures of enormous size that are nevertheless composed almost entirely of the simplest, most fundamental elements: hydrogen and helium, the building blocks of stars and the raw material of creation. Saturn's rings are perhaps its most iconic feature, the characteristic that makes it instantly recognizable even to casual observers. Through a small telescope, they appear as elegant extensions of the planet, bright and flat, catching sunlight in a way that no other structure in the solar system quite manages. But what we see as solid arcs of light are actually something far more complex and delicate. Billions upon billions of individual particles, each following its own orbit around Saturn, collectively creating the illusion of solidity. The rings extend outward from Saturn in a disk that spans an enormous diameter. From the innermost D ring to the outermost E ring, the ring system reaches approximately 175,000 miles or 282,000 kilometers from the planet. To put this in perspective, the distance from the Earth to the Moon is about 238,000 miles. Saturn's ring system, if oriented toward Earth, would extend more than halfway from our planet to our Moon. Yet, despite this vast width, the rings are astonishingly thin. The main rings, the bright, dense rings that dominate our view, have a typical thickness of only about 30 feet or 10 meters. Some estimates suggest they may be even thinner in places, perhaps as little as 30 feet at their thickest. Imagine a structure more than 280,000 kilometers across, but only 10 meters thick. The ratio of diameter to thickness is so extreme that if you made a scale model of Saturn's rings out of paper, the paper would be thousands of times too thick to be proportionally accurate. This thinness is maintained by the ring's own dynamics. Particles that stray above or below the ring plane are drawn back by collisions with other particles and by the gravitational pull of the ring system as a whole. Over time, these forces flatten any structure, creating the remarkably planar disk we observe. The rings lie precisely in Saturn's equatorial plane, aligned with the planet's rotation. This is no coincidence. Saturn's gravitational field is not perfectly spherical. The planet's rotation creates an equatorial bulge, and this slightly oblate field encourages particles to orbit in the equatorial plane. The rings are named alphabetically, not in order from the planet outward, but in the order they were discovered. Starting from Saturn and moving outward, we have the D ring, the C ring, the B ring, the Cassini division, the A ring, the F ring, the G ring, and the E ring. The Cassini division, despite its name, is not empty but contains fainter ring material. It appears as a dark gap when viewed from Earth because the particle density there is much lower than in the adjacent A and B rings. The D ring is tenuous and difficult to see, extending from the planet's cloud tops out to about 67,000 kilometers from Saturn's center. The C ring, sometimes called the crepe ring because of its gauzy appearance, extends from the outer edge of the D-ring to about 92,000 kilometers. It is darker and less opaque than the B-ring that lies beyond it. The B-ring is the brightest and most massive of Saturn's rings. It extends from approximately 92,000 to 118,000 kilometers from Saturn's center. The B-ring is so densely packed with particles that it is nearly opaque in places. When the Cassini spacecraft passed behind the B-ring from Earth's perspective, radio signals transmitted from the spacecraft were almost completely blocked, indicating that this ring contains the bulk of the material in the entire ring system. Beyond the B-ring lies the Cassini division, a gap about 4,700 kilometers wide. This division is not caused by a lack of material, but by a gravitational resonance with Saturn's moon Mimas. Particles that orbit in the Cassini division complete one orbit in exactly half the time it takes Mimas to complete its orbit. This means that particles there receive regular gravitational tugs from Mimas at the same point in their orbit, which gradually pushes them out of the division. The result is a cleared region, though it still contains some diffuse ring material. The A-ring lies outside the Cassini division, extending from about 122,000 to 137,000 kilometers from Saturn. Like the B-ring, it is bright and relatively opaque, though not quite as dense. The outer edge of the A-ring is sharply defined, maintained by gravitational resonances with small moons that orbit just outside the ring. The F-ring is a narrow, complex ring that lies just beyond the A-ring. It is only about 30 to 500 kilometers wide, but it shows remarkable structure with kinks, braids, and clumps that change over short timescales. The F-ring is shepherded by two small moons, Prometheus and Pandora, which orbit just inside and outside the ring and help confine its particles through gravitational interactions. The G-ring and E-ring are much fainter and more extended. The E-ring is particularly notable because it extends from about 180,000 to nearly 500,000 kilometers from Saturn, making it the widest ring in the system. The E-ring is continuously replenished by water ice particles erupting from geysers on Saturn's moon Enceladus. Without this source, the E-ring would dissipate in a relatively short time, perhaps 10,000 to 1 million years. What are the rings made of? Spectroscopic analysis, confirmed by direct measurements from spacecraft, reveals that the rings are composed of 99.9% pure water, ice. The remaining fraction of 1% includes silicate dust and possibly organic compounds that give some rings a slightly reddish tint, but the overwhelming majority of the material is ice. The particles themselves range in size from tiny grains smaller than a grain of sand to chunks as large as houses. The exact size distribution varies across the ring system. The C-ring and Cassini division appear to have a higher proportion of small particles, which is why they appear darker. Small particles scatter light less efficiently than larger ones. The B and A rings contain more large particles and are consequently brighter. These particles are not stationary. Each one orbits Saturn independently, following Kepler's laws of orbital motion. Particles closer to Saturn orbit faster than particles farther out. The innermost particles in the D-ring complete an orbit in about 4 to 5 hours, while particles in the outer A-ring take about 14 hours. This differential motion creates shearing forces across the rings, preventing particles from clumping together permanently, though temporary aggregations can form and dissolve continuously. Collisions between particles are common and generally gentle. When particles collide at low speeds, they may stick together temporarily, but further collisions or gravitational tugs from Saturn's moons break them apart again. These collisions also help dissipate energy from the system, causing the ring plane to remain flat and the orbits of particles to become more circular over time. The total mass of all the ring material combined is surprisingly small. Measurements from the Cassini spacecraft's final orbits, when it flew between the rings and Saturn's atmosphere, allowed scientists to determine the ring's mass by observing their gravitational effect on the spacecraft. The result was about 1.54 times 10 to the 19th kilograms, which sounds large but is only about 0.4 times the mass of Saturn's moon Mimas. This is roughly equivalent to 2/3 the mass of Earth's Antarctic ice sheet, spread across a surface area 80 times larger than Earth's entire surface. This low total mass has implications for understanding the ring's age and origin. If the rings formed billions of years ago along with Saturn, they would have been bombarded continuously by micrometeoroids, tiny particles of dust and rock that drift through the solar system and inevitably collide with any large structure. Such bombardment would darken the rings over time as non-icy material accumulated. The fact that the rings are so pure and bright suggests either that they are young, perhaps only 100 to 400 million years old, forming long after Saturn itself, or that they have some mechanism for shedding or rejecting the dark material that falls onto them. Recent research has explored this question from different angles. Some scientists argue that high-speed micrometeoroid impacts could vaporize incoming material, creating charged particles that are then swept away by Saturn's magnetic field before they can be incorporated into the ring system. This process might allow old rings to remain clean and bright, suggesting the rings could potentially be as old as Saturn itself, around 4.5 billion years. Other scientists point to the ring's low mass and the observation that ring material appears to be slowly falling into Saturn's atmosphere as evidence that the rings are geologically young. If the rings lose material over time, they must have been more massive in the past, and calculations suggest that if they formed billions of years ago, they would have started with much more mass than seems plausible. The debate continues, with new data and modeling constantly refining our understanding. What is clear is that the rings we see today are a dynamic system, not a static structure. Ring particles are continuously interacting with each other, with Saturn's moons, with the planet's magnetosphere, and with the solar wind. The rings are constantly changing, though on timescales so long that human observation captures only the tiniest moment in their evolution. Embedded within the rings are transient structures that come and go. Cassini observed what are called propeller structures, small gaps and clumps created by moonlets embedded in the ring material. These moonlets, too small to be seen directly, carve out regions around themselves, creating patterns that look like airplane propellers when viewed from above. There are also spokes, radial features in the B ring that rotate with Saturn's magnetosphere rather than with the ring particles themselves. These spokes are thought to be caused by dust grains that become electrically charged and levitate above the ring plane, possibly due to lightning in Saturn's atmosphere or micrometeoroid impacts. The rings interact with Saturn's magnetic field in complex ways. As Saturn's magnetic field rotates with the planet, it drags charged particles in the ionosphere with it. These particles can collide with and charge ring particles, particularly small dust grains. Once charged, these particles experience forces from the magnetic field that can lift them out of the ring plane or alter their orbits. This interaction creates a connection between the rings and Saturn's upper atmosphere, with material slowly spiraling inward and eventually falling into the planet as a kind of ring rain. Looking at Saturn's rings today, we are seeing a structure that may be young or ancient, that is certainly dynamic, and that will not last forever. Even if the rings formed with Saturn billions of years ago, they will eventually be lost. Ring material is slowly spiraling inward, either through interactions with Saturn's atmosphere or through the gradual loss of orbital energy due to collisions and tidal forces. Scientists estimate that the rings will be gone in perhaps 100 to 300 million years. A long time by human standards, but a brief moment in the lifespan of a planet. And so the rings hang in space around Saturn, a vast structure made of countless individual particles, each following the laws of orbital mechanics, collectively creating one of the most beautiful sights in the solar system. They are a reminder that complexity can emerge from simple rules, that beauty can arise from physics, and that even structures that appear solid and permanent are, in truth, temporary arrangements of matter that will change and eventually vanish given enough time. Saturn's atmosphere is a complex multi-layered system where weather unfolds on scales both vast and slow. What we see when we observe Saturn, the pale golden color, the faint bands that circle the planet, the occasional white storm, is only the uppermost layer of a gaseous envelope that extends down hundreds of kilometers before transitioning into liquid hydrogen. Understanding this atmosphere requires looking at its composition, its structure, its dynamics, and the processes that shape its appearance. The visible layer of Saturn's atmosphere consists primarily of hydrogen molecules, molecular hydrogen, or H2, making up approximately 96.3% by volume. Helium accounts for about 3.25%. The remaining fraction includes trace gases, methane at about 4,500 parts per million, ammonia at about 125 parts per million, and smaller amounts of water vapor, phosphine, hydrogen deuteride, ethane, acetylene, and other hydrocarbons. These minor constituents, though present in tiny quantities, play an outsized role in creating the clouds and hazes we observe. Temperature in the atmosphere decreases with altitude in the region we can see. At the level where atmospheric pressure equals 1 bar, a pressure similar to sea level on Earth, the temperature is approximately 134 Kelvin, or minus 139 degrees Celsius. Higher up, where the pressure drops to 0.1 bar, the temperature falls to about 84 Kelvin, or minus 189 degrees Celsius. These frigid temperatures mean that many compounds that would be gases on Earth condense into solid or liquid particles in Saturn's atmosphere, forming clouds. The cloud structure is layered, with different compounds condensing at different altitudes depending on temperature and pressure. The uppermost visible clouds are made of ammonia ice crystals. These clouds form at levels where the pressure is between 0.5 and 2 bar and the temperature ranges from 100 to 160 Kelvin. Ammonia ice is white, and these high-altitude clouds give Saturn much of its pale, muted appearance. Below the ammonia cloud layer, at pressures of about 2.5 to 9.5 bar, water ice clouds form. The temperatures at these depths range from 185 to 270 Kelvin. Intermixed with the water ice clouds is a layer of ammonium hydrosulfide ice, which forms at pressures of 3 to 6 bar and temperatures of 190 to 235 Kelvin. These deeper cloud layers are not directly visible from space because the ammonia clouds above them obscure our view, but their presence has been inferred from models and from occasional deep storms that punch through the upper layers. The atmosphere's appearance is dominated by band structures, alternating zones and belts that circle the planet parallel to the equator. These bands are created by east-west winds called zonal jets. Unlike Earth, where wind patterns are disrupted by continents and oceans, Saturn has no solid surface, allowing its wind patterns to persist with remarkable stability. The zonal jets on Saturn can reach speeds of 500 meters per second or about 1,800 kilometers per hour, particularly in the equatorial region. These are some of the fastest winds in the solar system. The mechanism that drives these winds is not fully understood, but it likely involves the combination of Saturn's rapid rotation and heat flowing up from the planet's interior. Saturn rotates once every 10.7 hours, which creates strong Coriolis forces that deflect moving air into east-west flows. Meanwhile, heat rising from the interior, remember that Saturn radiates more energy than it receives from the Sun, drives convection, creating upwelling in some regions and downwelling in others. The interaction of rotation and convection organizes the atmosphere into the banded pattern we observe. The bands are not all identical. Some appear brighter, others darker. The brightness differences are thought to arise from variations in cloud height and composition. Brighter zones may have higher, thicker ammonia clouds, while darker belts may allow us to see deeper into the atmosphere where clouds are thinner or composed of different materials. The exact colors we see, the subtle golds and tans, come from trace amounts of chemicals, possibly phosphorus compounds or complex organic molecules created by sunlight breaking apart methane and ammonia in the upper atmosphere. Saturn's atmosphere is less visually dramatic than Jupiter's. The bands are fainter, the color contrasts are more subtle, and large storms are less frequent. This difference is partly due to the thicker haze layer above Saturn's clouds. The haze, composed of tiny particles created by photochemical reactions in the upper atmosphere, scatters light and mutes the features below it. It also means that sunlight has to penetrate through more material before it reaches the main cloud deck, and this reduces the visual contrast between different regions. Despite this generally calm appearance, Saturn's atmosphere does host powerful storms. About once every 30 years, roughly once per Saturnian year, a massive storm erupts in the northern hemisphere. These great white spots, as they are called, appear as bright white ovals that expand rapidly, eventually encircling much of the planet. The storms are thought to be triggered by seasonal changes. As Saturn's northern hemisphere transitions from winter to spring and summer, the increasing solar heating may destabilize the atmosphere, triggering deep convection that brings material from lower layers up to the visible cloud tops. The most recent great white spot was observed in 2010. It began as a small bright spot but grew rapidly, developing a turbulent structure and eventually stretching around the entire planet. The storm persisted for months before slowly dissipating. Analysis of the storm showed that it brought ammonia ice from deep in the atmosphere up to the visible cloud tops, creating the bright white appearance. It also generated enormous lightning bolts, detected by the Cassini spacecraft as radio bursts called Saturn electrostatic discharges. In addition to these rare giant storms, Saturn's atmosphere contains smaller storms and vortices. Some appear as white spots, others as dark ovals. These features come and go over timescales of weeks to months, driven by atmospheric dynamics we are still working to understand. The Cassini mission observed many such storms, tracking their evolution and measuring their wind speeds, temperatures, and composition. The polar regions of Saturn show particularly interesting atmospheric structures. At the North Pole, there is the famous hexagonal jet stream, a six-sided wave pattern about 30,000 kilometers across. Each side of the hexagon is approximately 14,500 kilometers long, longer than Earth's diameter. The hexagon rotates with a period of 10 hours, 39 minutes, 24 seconds, which matches the period of radio emissions from Saturn's interior and is thought to represent the rotation rate of the planet's deep interior. The hexagon was first observed by the Voyager spacecraft in 1980 and 1981, and it has persisted for decades, as confirmed by Cassini observations starting in 2004. The longevity of this structure is remarkable. It has maintained its shape through seasonal changes and shows no signs of dissipating. Scientists have created laboratory experiments and computer models that demonstrate how such a structure can form from the interaction of winds at different speeds, but the precise mechanism that creates and maintains Saturn's hexagon is still being studied. At the center of the hexagon lies a vortex, a massive circulating storm similar to a hurricane. This polar vortex rotates in the same direction as the hexagon itself and has sustained winds of approximately 150 meters per second. Unlike Earth's hurricanes, which draw their energy from warm ocean water and dissipate when they move over land, Saturn's polar vortex is driven by internal heat and has no surface to disrupt it. It could persist for centuries or millennia. The south pole of Saturn also has a vortex, though without the hexagonal structure. This southern vortex has been studied extensively by Cassini. Images reveal a dark eye surrounded by a swirling wall of clouds with wind speeds reaching 550 kilometers per hour. The eye is about 8,000 kilometers across, roughly two-thirds the size of Earth. This vortex, like its northern counterpart, is warm compared to the surrounding atmosphere, suggesting that it extends deep into the planet's interior. Temperature variations across Saturn's atmosphere reveal more about its structure and energy balance. The equatorial region is slightly warmer than the poles, but the temperature differences are small compared to Earth. This is because Saturn's main heat source is internal rather than solar. The planet radiates approximately 2.5 times more energy than it absorbs from the Sun, meaning that most of the atmospheric heating comes from below, from heat slowly escaping the planet's interior. This internal heat source helps drive the convection and wind patterns we observe. The upper atmosphere of Saturn, above the main cloud deck, is called the thermosphere. Here, temperatures actually increase with altitude due to absorption of ultraviolet light from the Sun and energy from charged particles trapped in Saturn's magnetosphere. The thermosphere can reach temperatures of several hundred Kelvin, far warmer than the cloud tops below, though the air is so thin that there is very little total heat content. At the very top of the atmosphere lies the exosphere, where the atmosphere gradually transitions into space. Molecules here are so far apart that they rarely collide. Some particles in the exosphere have enough energy to escape Saturn's gravity entirely, creating a very slow atmospheric leakage. This process of atmospheric escape is negligible compared to Saturn's total atmospheric mass, but over billions of years it represents a gradual loss of material. The composition of the atmosphere provides clues about Saturn's formation and evolution. The hydrogen to helium ratio, as mentioned earlier, is depleted in helium compared to the primordial solar nebula. This supports the idea that helium is raining out deep in the planet's interior. The trace gases, methane, ammonia, water, are enriched compared to solar abundances, suggesting that Saturn captured not just gas from the nebula, but also incorporated icy planetesimals during its formation. These ices vaporized in the planet's hot interior and mixed into the atmosphere. The atmospheric chemistry is complex. Sunlight breaks apart methane molecules in the upper atmosphere, creating a variety of hydrocarbons. These include ethane, acetylene, propane, and more complex molecules. Some of these hydrocarbons condense into haze particles, creating the diffuse haze layer that overlies Saturn's clouds. Others react further, potentially forming even more complex organic molecules. The study of this chemistry is relevant not just for understanding Saturn, but for understanding the chemistry of atmospheres in general, including those of exoplanets and moons in our own solar system. Lightning in Saturn's atmosphere is another fascinating phenomenon. Unlike Earth, where lightning occurs primarily in association with water clouds, lightning on Saturn appears to originate from the water cloud layer deep in the atmosphere. The electrical discharges are powerful, producing radio waves that can be detected by spacecraft. These radio bursts, called Saturn electrostatic discharges, or SEDs, were first detected by the Voyager missions and studied in detail by Cassini. They occur in storms that persist for days or weeks, and their intensity and frequency provide information about convection deep in the atmosphere where we cannot see directly. The atmosphere also interacts with Saturn's rings and moons. Material from the rings slowly falls into Saturn's upper atmosphere, creating a kind of ring rain. This material is mostly water ice, and as it falls into the warmer lower atmosphere, it vaporizes. Cassini's final dives between the rings and Saturn's cloud tops detected this rain directly, observing the complex organic molecules that form when ring material enters the atmosphere. The influx of material from the rings may influence the chemistry and composition of Saturn's upper atmosphere, though the total amount is small. Similarly, geysers on the Moon, Enceladus eject water vapor and ice particles that escape the Moon's gravity and spread throughout the Saturn system. Some of this material eventually falls into Saturn's atmosphere, adding water to the planet's overall composition. This connection between the rings, the moons, and the atmosphere shows that the Saturn system is not a collection of isolated objects, but an interconnected whole, with material flowing between components over time. Looking at Saturn's atmosphere as a whole, we see a system in constant motion, but also in a state of long-term stability. The winds have been blowing in the same patterns for decades, likely for centuries. The hexagon has persisted through at least one complete Saturnian year. The banded structure remains fundamentally unchanged even as individual storms come and go. This stability arises from the basic physics of a rapidly rotating gas giant with internal heat. The same processes that created the atmosphere's current state 4 billion years ago are still operating today, creating a kind of equilibrium that persists even as the details constantly evolve. And within this equilibrium, there is always something happening. Storms develop and fade. Lightning crackles deep in the clouds. Hazes form and drift. Temperature patterns shift slightly with the seasons. The atmosphere breathes, in a sense, as heat flows from the interior, as sunlight warms the day side and cools the night side, as charged particles from space rain down into the polar regions. It is a living system in the sense that it is constantly changing, constantly processing energy, constantly creating structure from the simple ingredients of hydrogen and helium and a few trace gases. At Saturn's North Pole, there exists a structure so unusual that it challenges our understanding of planetary atmospheres. This is the hexagonal jet stream, a six-sided wave pattern in Saturn's northern hemisphere that has been observed for more than 40 years and shows no signs of changing or dissipating. The hexagon is a reminder that the universe can create geometries and patterns that seem too perfect, too regular, to occur naturally, yet they arise from the fundamental physics of fluid dynamics and rotation. The hexagon is enormous. Each of its 6 sides stretches approximately 14,500 kilometers, making the total perimeter roughly 87,000 kilometers, more than twice Earth's circumference. The structure encompasses the North Polar region from about 75 to 80 degrees latitude. Within this hexagonal ring flows a powerful jet stream, an eastward moving river of air with wind speeds reaching 320 kilometers per hour, or roughly 200 miles per hour. The hexagon was discovered by the Voyager missions when they flew past Saturn in 1980 and 1981. Voyager's cameras captured images of Saturn's North Pole that revealed this remarkable 6-sided structure. At the time, it was winter in Saturn's northern hemisphere, and the pole was in shadow, making detailed observations difficult. The hexagon appeared as a dark feature defined by its clouds, rotating with a period of about 10 hours, 39 minutes. For 25 years, the hexagon remained unobserved as Saturn's northern hemisphere slowly transitioned from winter to spring. No spacecraft visited Saturn during this period, and Earth-based telescopes could not see the polar region clearly due to the planet's axial tilt. When the Cassini mission arrived at Saturn in 2004, one of its objectives was to determine whether the hexagon still existed or whether it had been a temporary feature unique to the season when Voyager observed it. Cassini confirmed that the hexagon not only still existed, but had maintained its shape with remarkable precision. The spacecraft's cameras and infrared instruments mapped the hexagon in detail, revealing its structure at multiple wavelengths and atmospheric levels. The hexagon persisted through Saturn's equinox in 2009, when the sun's illumination shifted from the southern to the northern hemisphere, and continued to be visible through the northern summer season that followed. The longevity of the hexagon is one of its most striking characteristics. It has been continuously observed for more than 4 decades, which represents more than 1 full Saturnian year. This tells us that the hexagon is not a weather phenomenon in the way we usually understand it, not a transient storm or seasonal feature, but a fundamental mode of the planet's atmospheric circulation. It is as much a part of Saturn's structure as the planet's rings or its system of moons. What creates the hexagon? The question has fascinated scientists since its discovery, and while we now have a good understanding of the basic physics involved, the details are still being refined. The hexagon is a type of atmospheric wave called a Rossby wave, which forms in rotating fluids when there are variations in the speed of rotation or in the fluid's depth. On Earth, Rossby waves create the meandering patterns of the jet stream that influence weather across the planet. On Saturn, a special configuration of these waves has produced a hexagonal standing wave. Computer simulations and laboratory experiments have demonstrated that hexagons can form spontaneously in rotating fluids under the right conditions. In the lab, researchers have created hexagons in rotating tanks of water by carefully controlling the speed of the rotation and introducing a cylindrical barrier. The fluid flows at different speeds inside and outside the barrier, and at the boundary between these regions, a hexagonal wave pattern emerges. Saturn's hexagon likely forms from a similar mechanism, with a jet stream at the boundary between 2 regions of the atmosphere rotating at different speeds. At the center of the hexagon is a vortex, a circulating storm that anchors the pattern. This polar vortex rotates in the same direction as the hexagon and has wind speeds that peak at about 150 meters per second. The vortex extends deep into the atmosphere, perhaps hundreds of kilometers down, and it is surrounded by a wall of clouds that defines the inner boundary of the hexagon. Outside the hexagon, at lower latitudes, the winds slow down, creating the speed differential that maintains the wave pattern. The hexagon rotates with a period of 10 hours, 39 minutes, and 24 seconds. This is significant because it matches the period of radio emissions from Saturn's interior, which are thought to be tied to the rotation of the planet's magnetic field and thus the rotation of the deep interior where the magnetic field is generated. The fact that the hexagon rotates at the same rate as the deep interior suggests that it is somehow coupled to layers far below the visible cloud tops, though the exact mechanism of this coupling is not fully understood. The hexagon is not uniform in altitude. Observations show that it tilts slightly, with the clouds on one side sitting higher than the clouds on the opposite side. This tilt rotates with the hexagon, creating a wave-like motion. Additionally, the hexagon shows vertical structure. Infrared observations reveal that the hexagonal pattern extends upward through multiple layers of the atmosphere, from the cloud tops where it was first observed up into the stratosphere. At higher altitudes, the hexagon becomes less distinct but is still present as a modulation in temperature and wind patterns. The color of the hexagon changed during Cassini's mission. Early in the mission, when it was still winter in the north, the hexagon appeared relatively blue compared to the rest of Saturn. As spring and summer arrived and sunlight began to illuminate the North Pole, the hexagon's color shifted to a golden hue, similar to the rest of the planet. This color change is thought to result from increased photochemical haze production as sunlight triggers chemical reactions in the upper atmosphere. The haze particles scatter light differently, changing the apparent color of the feature. Within the hexagon, there are smaller features and structures. Cassini observed small vortices and wave patterns embedded in the hexagonal jet stream. Some of these rotate in the same direction as the overall flow, others in the opposite direction. These smaller features may be analogous to eddies in Earth's atmospheric and oceanic currents, transient structures that form from instabilities in the flow and then dissipate. The walls of the hexagon, the edges where the jet stream flows, are not perfectly straight lines but show small ripples and waves. These perturbations may be caused by interactions between the jet stream and the deeper layers of the atmosphere, or they may result from the hexagon adjusting to changes in the atmospheric temperature and pressure distribution as seasons change. Despite these small variations, the overall hexagonal shape remains remarkably stable. One of the most intriguing questions about the hexagon is why it has this particular shape. Why a hexagon and not a pentagon, heptagon, or some other polygon? The answer lies in the stability of wave patterns in rotating fluids. Mathematical analysis shows that certain wave patterns are more stable than others, and hexagons happen to be particularly stable for the specific conditions present at Saturn's North Pole. The number of sides in the polygon is related to the ratio of wind speeds inside and outside the jet stream and to the width of the jet stream itself. Change these parameters slightly and you might get a different shape, but for Saturn's actual conditions, a hexagon is what forms. Interestingly, Saturn's south pole does not have a hexagon. Instead, the south pole is dominated by a circular vortex with a distinct eye, more similar to a hurricane. This difference between the north and south poles is not fully understood. It may be that the southern vortex is simply a different stable configuration, or it may be that the hexagon requires specific conditions that happen to be present in the north, but not in the south. Seasonal changes might also play a role, and it is possible that the southern hemisphere could develop a hexagonal pattern at a different point in Saturn's year though observations have not yet shown this. The hexagon's temperature structure provides additional insights. Infrared measurements show that the air within the hexagon is warmer than the surrounding regions at the same latitude but outside the hexagonal boundary. This temperature difference is small, only a few degrees, but it is consistent and extends through multiple atmospheric layers. The warmth suggests that there is enhanced downwelling within the hexagon, where air from higher altitudes descends and compresses, heating as it does so. This vertical motion could be part of what maintains the vortex at the hexagon's center. The energy that sustains the hexagon must come from somewhere. Unlike Earth's jet streams, which are driven primarily by the temperature difference between the equator and the poles created by solar heating, Saturn's hexagon is thought to be maintained by heat flowing from the planet's interior. Saturn radiates more heat than it receives from the Sun, and this internal heat drives convection deep in the atmosphere. As warm air rises and cool air sinks, organized circulation patterns form, and the hexagon is one manifestation of this deep convection coupled with the planet's rapid rotation. There is also the possibility that the hexagon interacts with Saturn's magnetic field. Charged particles trapped in Saturn's magnetosphere can deposit energy into the upper atmosphere, particularly near the poles. This auroral heating might influence the atmospheric circulation and contribute to maintaining the polar vortex and the hexagonal jet stream around it. Cassini's observations of Saturn's auroras showed that they occur within the hexagon, confirming that there is indeed a connection between the magnetosphere and the polar atmosphere. Looking at the hexagon from a broader perspective, it is a beautiful example of self-organization in nature. No external force shapes it into a hexagon. The shape emerges naturally from the laws of fluid dynamics and the specific conditions on Saturn, the planet's rotation rate, the atmospheric composition, the internal heat flow, the distribution of winds at different latitudes. Given these conditions, a hexagon forms, and it remains stable year after year, decade after decade. And so the hexagon continues to rotate at Saturn's North Pole, a geometric pattern etched in flowing gas, maintained by processes we are only beginning to fully understand. It is a feature that no human being will ever see in person, that exists on a world nearly 1 billion miles from Earth, yet we have studied it in detail, mapped its structure, tracked its evolution, and come to appreciate it as one of the many wonders that our solar system contains. The hexagon is a reminder that the universe operates according to rules that produce outcomes both beautiful and strange, and that even a simple fluid like hydrogen, when given the right conditions, can create patterns of remarkable complexity and order. Saturn, like several other planets in our solar system, possesses a magnetic field. This field extends far beyond the planet itself, creating a region of space called the magnetosphere, where charged particles from the Sun and from Saturn's moons are trapped and shaped by magnetic forces. Understanding Saturn's magnetic field helps us understand the planet's interior structure, its interaction with the solar wind, and the environment in which its moons orbit. The strength of Saturn's magnetic field at the planet's equator is approximately 21 microtesla, which is about 580 times weaker than Earth's magnetic field at Earth's equator. Despite being weaker than Earth's field in absolute terms, Saturn's magnetosphere is the second largest structure in the solar system after Jupiter's, extending millions of kilometers into space. On the side facing the Sun, the magnetosphere is compressed by the solar wind and extends to about 20 Saturn radii, or about 1.2 million kilometers. On the night side, the magnetosphere stretches into a long tail, called the magnetotail that extends for hundreds of Saturn radii, possibly reaching past the orbit of Titan. Saturn's magnetic field has a unique property. It is nearly perfectly aligned with the planet's rotation axis. The angle between the magnetic axis and the rotation axis is less than 1 degree, making Saturn's field the most symmetrical of any planet in the solar system. Earth's magnetic field is tilted about 11 degrees from its rotation axis, and Uranus's field is tilted an extraordinary 98.6 degrees. Saturn's near-perfect alignment was unexpected and remains somewhat mysterious. The origin of Saturn's magnetic field, like that of other planets with strong fields, is believed to be a dynamo process in the planet's interior. Deep inside Saturn, at depths where the pressure is high enough to transform hydrogen into its metallic state, the metallic hydrogen can conduct electricity. As Saturn rotates, this conducting fluid moves in complex patterns driven by convection currents as heat flows from the planet's core toward the surface. The motion of this electrically conducting fluid generates electric currents, and these currents create magnetic fields. The field lines loop through the planet and extend out into space, creating the magnetosphere we observe. The fact that Saturn's magnetic field is so well aligned with its rotation axis tells us something about the interior structure. The dynamo that generates the field must be operating in a region that is symmetric with respect to the rotation axis. This could mean that the metallic hydrogen layer is relatively uniform and that the convection patterns within it are organized primarily by rotation. In contrast, Earth's tilted field suggests that our planet's core has some asymmetry or that the convection patterns are more complex. Saturn's magnetosphere is filled with charged particles, electrons, and ions that come from several sources. The solar wind, a stream of charged particles constantly flowing outward from the Sun, provides some of these particles. When the solar wind encounters Saturn's magnetosphere, most of it is deflected around the magnetosphere, but some particles can enter through processes called magnetic reconnection that occur at the boundary. Once inside the magnetosphere, these particles become trapped by the magnetic field lines and spiral along them. Another major source of particles in Saturn's magnetosphere is the planet's moon Enceladus. Enceladus, as we will discuss in detail later, has geysers that erupt water vapor and ice particles from its south polar region. These eruptions eject material at speeds high enough that some of it escapes Enceladus's weak gravity and enters orbit around Saturn. The ice particles remain in orbit and form Saturn's E-ring, but the water vapor becomes ionized by ultraviolet light from the Sun or by electron impacts, creating ions of oxygen and hydrogen that are then picked up by Saturn's magnetic field. The presence of these water group ions, ions derived from water molecules, gives Saturn's magnetosphere a unique character. In the region between Saturn and the orbit of Enceladus, the magnetosphere is dominated by these ions, creating what is sometimes called a water cloud. The density of ions in this region can be quite high, and the ions interact with Saturn's magnetic field, causing the field to rotate with the planet and dragging the ions along with it. This co-rotation of the magnetosphere with Saturn is maintained by the planet's ionosphere, a layer of electrically charged particles in the upper atmosphere. Magnetic field lines that connect to the ionosphere effectively lock the nearby magnetosphere to the planet's rotation. As Saturn spins, the magnetic field lines sweep through space, and any charged particles attached to those field lines are forced to rotate with them. However, as you move farther from Saturn, maintaining co-rotation requires more and more energy because the particles must be accelerated to higher speeds. Eventually, at a certain distance, the magnetosphere can no longer enforce co-rotation, and the particles begin to slip relative to the magnetic field. Cassini observed the boundary between the co-rotating region and the outer magnetosphere in detail. This boundary is not sharp, but rather a transition zone where the flow patterns change. Inside the boundary, particles rotate with Saturn. Outside, they flow more slowly and are more influenced by the solar wind. The location of this boundary varies depending on the pressure of the solar wind. When the solar wind is strong, it compresses the magnetosphere and pushes the boundary inward. When the solar wind is weak, the boundary expands outward. The particles trapped in Saturn's magnetosphere are not stationary. They move in complex ways, spiraling along magnetic field lines, drifting around the planet, and bouncing back and forth between the north and south magnetic poles. The paths they follow are determined by the interplay of magnetic forces, the planet's rotation, and their own energy. Some particles eventually collide with Saturn's moons or rings and are lost from the system. Others are accelerated to very high energies and become part of Saturn's radiation belts. Saturn's radiation belts are regions where high-energy electrons and ions are trapped by the magnetic field. These particles pose a hazard to spacecraft. Cassini had to be carefully designed to withstand the radiation it would encounter during its many orbits through Saturn's magnetosphere. The radiation is most intense in the inner magnetosphere, close to the planet, where the magnetic field is strongest and where particles can be accelerated to the highest energies. The interaction between Saturn's magnetosphere and its rings is particularly interesting. The rings orbit within the magnetosphere, and they act as a sink for charged particles. Particles that drift inward and encounter ring material are absorbed, creating a gap in the radiation belts. This gap, observed by spacecraft, provides evidence that the rings are effective at removing particles from the magnetosphere. It also means that the ring particles are constantly being bombarded by energetic particles, which can sputter material from their surfaces and change their composition over time. At Saturn's poles, the magnetosphere creates auroras, just as it does on Earth. When charged particles from the magnetosphere are accelerated along magnetic field lines and crash into the upper atmosphere, they excite atoms and molecules, causing them to emit light. On Saturn, these auroras occur in the ultraviolet and infrared parts of the spectrum, invisible to human eyes but detectable by spacecraft instruments. Cassini observed Saturn's auroras extensively, mapping their location and intensity, and studying how they respond to changes in the solar wind. Saturn's auroras are generally circular, surrounding each pole, and they occur within the region of the polar hexagon in the north and within the southern polar vortex in the south. The auroras are not constant, but flicker and brighten in response to dynamic processes in the magnetosphere. Sometimes they appear as narrow rings, other times they expand and diffuse. These changes reflect variations in the rate at which particles are being accelerated and funneled into the atmosphere. The connection between the magnetosphere and the ionosphere creates what is called an electrodynamic coupling. Electric currents flow along magnetic field lines between the magnetosphere and the ionosphere, transferring energy and momentum. These currents can be millions of amperes, creating significant electromagnetic effects. They heat the ionosphere, influence atmospheric circulation, and drive some of the complex dynamics observed in the polar regions. One of the enduring mysteries about Saturn's magnetosphere is the origin of its radio emissions. Saturn emits radio waves at a specific period of 10 hours, 39 minutes and 24 seconds, and this period was originally thought to represent the rotation rate of the planet's interior. However, later observations showed that the radio period is not constant but varies slightly over time, sometimes speeding up and sometimes slowing down by as much as 1%. This variability suggests that the radio emissions are not tied directly to the planet's interior rotation, but are instead influenced by processes in the magnetosphere or interactions with the solar wind. Despite extensive study by the Cassini mission, the exact mechanism that generates Saturn's radio emissions remains unclear. They are thought to arise from a process called cyclotron massa instability, where electrons gyrating in the magnetic field emit radio waves, but the conditions that trigger and modulate these emissions are not fully understood. Understanding this phenomenon is important because similar radio emissions are observed from other magnetized planets and from astronomical objects beyond our solar system. Saturn's magnetosphere also interacts with Titan, the planet's largest moon. Titan orbits outside the main magnetosphere most of the time, but it periodically passes through the magnetotail and is exposed to Saturn's magnetic field and the particles trapped within it. Titan has a thick atmosphere, and when magnetospheric particles collide with this atmosphere, they create a complex interaction region. The magnetic field drapes around Titan, and electric currents flow in the Moon's ionosphere. This interaction removes energy from the magnetosphere and deposits it in Titan's upper atmosphere, influencing the Moon's atmospheric chemistry and contributing to its slow atmospheric loss. The study of Saturn's magnetosphere reveals it to be a dynamic, complex system shaped by the planet's internal dynamo, its rotation, the influx of material from its moons, and the pressure of the solar wind. It is a region where magnetic fields organize matter and energy, where processes occur that have no counterpart on Earth, and where the physics of plasmas and electromagnetic interactions can be studied in detail. It is also a region that connects the different parts of the Saturn system, linking the planet's interior to its moons, its rings, and the surrounding space. Saturn's relationship with time unfolds on scales both short and long. The planet rotates rapidly, spinning once on its axis every 10 hours and 39 minutes, creating a day far shorter than Earth's 24-hour cycle. Yet, it orbits the Sun slowly, completing one revolution every 29.4 Earth years, making a Saturnian year almost 3 decades long. This contrast between rapid rotation and slow orbital motion shapes much of what we observe about Saturn and influences the planet's structure, its atmospheric dynamics, and its seasonal changes. Let us start with rotation. Saturn completes one full rotation in approximately 10.7 hours, though the exact period depends on which part of the planet you measure. Unlike a solid body such as Earth, where all parts rotate at the same rate, Saturn is a fluid world. Different latitudes rotate at different speeds, a phenomenon called differential rotation. The equatorial region completes a rotation in about 10 hours and 14 minutes, while regions at higher latitudes take slightly longer, up to about 10 hours and 40 minutes near the poles. This differential rotation is made possible by the fact that Saturn has no solid surface. The atmosphere at different latitudes can move independently, creating the banded wind patterns we observe. The rotation period we typically quote, 10.7 hours, is an average based on observations of the planet's magnetic field and radio emissions, which are thought to be tied to the rotation of the deep interior where the magnetic field originates. The rapid rotation has profound effects on Saturn's shape. The centrifugal force generated by this rapid spin causes the equator to bulge outward and the poles to flatten. Saturn's equatorial radius is approximately 60,300 kilometers, while its polar radius is only about 54,000 kilometers. This means the planet is about 6,300 kilometers wider at the equator than from pole to pole, a difference of roughly 10%. Saturn is the most oblate planet in the solar system, more flattened than even Jupiter, despite Jupiter being more massive and rotating almost as quickly. The rapid rotation also organizes the atmospheric circulation into the east-west banded pattern we observe. The Coriolis force, which arises from rotation and affects the motion of fluids on rotating bodies, deflects north-south winds into east-west flows. On Earth, this creates our jet, streams, and trade winds. On Saturn, it creates the powerful zonal jets that circle the planet, maintaining the stable band structure that persists year after year. Now consider Saturn's orbit. Saturn circles the Sun at an average distance of about 886 million miles, or 1.427 billion kilometers. This is 9.5 times the distance from Earth to the Sun. In astronomical units, Saturn orbits at 9.5 AU. At this distance, sunlight is much weaker than it is at Earth. The intensity of sunlight falls off with the square of the distance, so at Saturn's distance, sunlight is only about 1% as intense as it is at Earth. This weak sunlight means that Saturn receives very little energy from the Sun compared to inner planets. The total solar energy reaching Saturn's cloud tops is only about 15 watts per square meter, compared to about 1,368 watts per square meter at Earth. Yet Saturn's total energy output, as measured by infrared observations, is about 46 watts per square meter. This means Saturn radiates about 3 times more energy than it absorbs from the Sun. The extra energy comes from the planet's interior, left over from its formation, and supplemented by the slow rain of helium mentioned earlier. Saturn's orbit is not a perfect circle, but an ellipse, though not a very elongated one. The orbit's eccentricity is 0.054, meaning the orbit is slightly oval. At perihelion, Saturn's closest approach to the Sun, it is about 1.353 billion kilometers from the Sun. At aphelion, its farthest point, it is about 1.504 billion kilometers away. This variation in distance is about 150 million kilometers, comparable to Earth's average distance from the Sun, yet it makes only a small difference in the sunlight Saturn receives because the planet is already so far away. Saturn takes 29.4 Earth years to complete one orbit. More precisely, Saturn's orbital period is 29 years, 167 days, 6 hours, and 42 minutes. This means that from our perspective on Earth, Saturn returns to the same position in the sky relative to the background stars only once every 3 decades. A person who lives to age 90 will see Saturn complete only 3 orbits during their lifetime. The slow orbital motion has implications for observing Saturn from Earth. Because Saturn moves slowly against the background stars, it remains in the same constellation for several years. Ancient astronomers noticed this and named Saturn after the Roman god of time, reflecting its slow, steady motion. The planet's visibility from Earth changes throughout its orbit due to the geometry of Earth's orbit and Saturn's orbit, but Saturn is usually visible for several months each year, moving gradually across the night sky. Saturn's axis of rotation is tilted relative to its orbital plane by 26.7 degrees. This axial tilt is similar to Earth's tilt of 23.5 degrees, and like Earth, the tilt creates seasons on Saturn. As Saturn orbits the Sun, different hemispheres receive more direct sunlight at different times. When the northern hemisphere is tilted toward the sun, it experiences summer, while the southern hemisphere experiences winter. Half an orbit later, 14.7 years, the situation reverses. These seasons are long by human standards. A Saturnian spring or summer lasts about 7 Earth years. Because Saturn's orbit has low eccentricity, the seasons are primarily driven by the axial tilt rather than by variations in distance from the sun. The northern and southern summers are approximately equally warm, unlike on Mars, where the orbit's higher eccentricity creates significant differences between northern and southern summers. Seasonal changes on Saturn are subtle but real. Temperature variations between summer and winter are small because the planet's main heat source is internal rather than solar. However, observations show that solar heating does influence the upper atmosphere and the middle atmosphere where the main cloud deck resides. During summer, the sunlit hemisphere's upper atmosphere warms slightly, creating small pressure differences that can influence wind patterns and cloud formation. The great white spot storms that erupt on Saturn roughly once every 30 years are thought to be triggered by seasonal changes. These massive storms appear in the northern hemisphere during the transition from winter to spring, suggesting that increasing solar heating destabilizes the atmosphere in some way, allowing deep convection to bring material up from lower levels and create the bright white clouds we observe. From our perspective on Earth, one of the most beautiful consequences of Saturn's axial tilt is the changing appearance of the rings. Because the rings lie in Saturn's equatorial plane, and because Saturn's axis is tilted, the rings appear from Earth to tilt back and forth over the course of Saturn's 29-year orbit. At one point in the orbit, we see the rings at their maximum opening, tilted toward us by about 27 degrees, showing their full splendor. 14.7 years later, we see the rings edge on, and because they are so thin, they almost vanish from view, appearing as a thin line across the planet's disk. These edge-on events, called ring plane crossings, occur twice per Saturnian year, once as the northern hemisphere transitions from autumn to winter, and again as it transitions from spring to summer. During ring plane crossings, Earth-based observers can sometimes detect small moons that are normally hidden in the glare of the rings. The most recent ring plane crossing occurred in 2009, and the next will not occur until 2025. The motion of Saturn through space is not just its orbit around the Sun, but also its participation in the larger motion of the solar system. The Sun itself orbits the center of the Milky Way galaxy, and Saturn goes along for the ride. The Sun, and with it the entire solar system, completes one galactic orbit roughly every 225 to 250 million years. This galactic year is so long that Saturn has completed only about 20 galactic orbits since it formed 4.6 billion years ago. On even larger scales, the Milky Way galaxy is moving through space as part of the local group of galaxies, which is itself moving toward a larger concentration of galaxies called the Great Attractor. Saturn, along with everything else in the solar system, participates in these motions, though they are far too slow and vast to influence the planet's immediate environment. Returning to more familiar timescales, consider what Saturn's rapid rotation and slow orbit mean for a hypothetical observer on the planet's cloud tops. A day would last only 10.7 hours. The Sun would rise and set roughly twice per Earth day, though the Sun would appear small and dim, only about 1/10 the apparent diameter it has from Earth. Over the course of a Saturnian year, that observer would experience about 24,000 sunrises and sunsets, though the seasonal changes would be gradual and subtle, barely perceptible on a day-to-day basis. The combination of rapid rotation and slow orbit creates a dynamic where short-term processes, atmospheric circulation, storm development, cloud formation, operate on timescales of hours to days, while long-term processes, seasonal changes, orbital variations, operate on timescales of years to decades. This separation of timescales is part of what makes Saturn such a stable, enduring world. The fast processes reach equilibrium quickly, while the slow processes change so gradually that the planet's overall character remains constant over human lifetimes. And so, Saturn turns in its orbit, a world where time operates on multiple scales simultaneously. Each rotation brings a new day in just over 10 hours. Each orbit takes nearly 3 decades. Both motions continue steadily, governed by the same gravitational laws that have shaped the solar system since its formation, creating rhythms that will persist for billions of years into the future. Among Saturn's many moons, one stands apart not just for its size, but for its remarkable similarity to Earth in certain fundamental ways. This is Titan, Saturn's largest moon and the second largest moon in the entire solar system. Titan is the only moon anywhere known to possess a thick atmosphere, and it is the only world besides Earth where stable bodies of liquid have been confirmed on the surface. These liquids are not water, but hydrocarbons, methane and ethane, yet they flow in rivers, collect in lakes, and evaporate back into the atmosphere in a cycle that mirrors Earth's water cycle, albeit at temperatures far below anything we experience. Titan was discovered by Dutch astronomer Christian Huygens on March 25, 1655. Huygens had been inspired by Galileo's discovery of Jupiter's 4 largest moons in 1610 and had worked with his brother to build increasingly powerful telescopes. Through one of these instruments, Huygens observed a faint point of light near Saturn and tracked it night after night, confirming that it was indeed a moon orbiting the ringed planet. He initially called his discovery Luna Saturni, Saturn's moon, though it would later be named Titan by John Herschel, drawing from Greek mythology. For centuries, Titan remained little more than a bright point of light, its true nature hidden. When the Voyager missions flew past Saturn in 1980 and 1981, they confirmed what astronomers had suspected. Titan has a substantial atmosphere. In fact, Titan's atmosphere is so thick and hazy that Voyager's cameras could not see the surface at all. The moon appeared as a featureless orange sphere, beautiful but frustratingly opaque. It was not until the Cassini spacecraft arrived at Saturn in 2004, carrying the Huygens probe, that we finally saw Titan's surface. Cassini used radar and infrared instruments to peer through the haze, revealing a complex landscape of dunes, mountains, and most remarkably, lakes and seas concentrated near the poles. On January 14, 2005, the Huygens probe descended through Titan's atmosphere and landed on the surface, becoming the most distant spacecraft landing ever achieved. The probe sent back images of a world that looked eerily familiar. Pale hills cut by dark channels flowing down to a flat plain, yet made of materials utterly alien. Titan orbits Saturn at a distance of approximately 1,222,000 kilometers, or about 760,000 miles. This places it far outside the main ring system in a relatively quiet region where it takes 15.9 Earth days to complete one orbit. Titan is tidally locked to Saturn, meaning it always shows the same face to the planet, just as our moon always shows the same face to Earth. The moon itself is substantial, with a diameter of about 5,150 kilometers, or 3,200 miles. This makes Titan larger than the planet Mercury, though less massive because Titan is composed primarily of water ice and rock, while Mercury is mostly metal and rock. If Titan orbited the Sun instead of Saturn, it might be classified as a planet in its own right. What makes Titan truly extraordinary is its atmosphere. The atmospheric pressure at Titan's surface is about 1.5 times that of Earth's sea level pressure, 60% greater than what we experience. This means that if you were standing on Titan, you would feel a pressure similar to what a person experiences swimming about 50 feet below the ocean surface on Earth. This is the only moon in the solar system with a substantial atmosphere, and the pressure is greater than that on any other moon or even some planets. The atmosphere is composed of about 95% nitrogen and about 5% methane by volume, with trace amounts of other compounds including hydrogen, ethane, propane, acetylene, and various other hydrocarbons. The nitrogen atmosphere is particularly interesting because nitrogen is relatively rare in the outer solar system in gaseous form. Scientists believe Titan's nitrogen came from ammonia that was present when the moon formed. Over time, sunlight and chemical processes broke apart the ammonia molecules, releasing nitrogen into the atmosphere. The methane in Titan's atmosphere is a puzzle. Sunlight continuously breaks down methane through photochemical reactions, splitting the molecules apart. Based on the rate of destruction, all of Titan's atmospheric methane should be depleted in about 10 million to 100 million years, a blink of an eye in geological terms. Yet Titan clearly has methane today, which means there must be some source replenishing it. The most likely explanation is that methane is released from Titan's interior, perhaps through cryovolcanism, volcanoes that erupt liquid water and ammonia instead of molten rock, or through outgassing from the subsurface. Recent research has suggested that Titan may have a methane clathrate crust, a layer of ice 5 to 10 kilometers thick, where methane molecules are trapped within the crystal structure of water ice. This crust could act as an insulating layer and as a reservoir for methane that slowly releases into the atmosphere over time. The presence of such a crust would explain both the source of atmospheric methane and certain features of Titan's surface, such as the shallow depth of impact craters. The atmosphere extends to remarkable heights. Because Titan's gravity is weaker than Earth's, about 14% of Earth's surface gravity, the atmosphere is not compressed as tightly and extends upward to about 600 kilometers or 370 miles above the surface. This is roughly 10 times higher than Earth's atmosphere extends. The upper atmosphere is filled with a complex haze of organic particles created when sunlight breaks apart methane and nitrogen molecules. These particles give Titan its characteristic orange color. At Titan's surface, the temperature is approximately 94 Kelvin, or minus 179 degrees Celsius. This is cold enough that water ice is as hard as rock, and liquid water cannot exist on the surface, except perhaps temporarily in impact craters or near cryovolcanic vents. But it is warm enough, thanks to some greenhouse warming from the atmosphere, that methane can exist as a liquid. Methane on Titan behaves much like water does on Earth. It evaporates from the surface, rises into the atmosphere, condenses into clouds, and falls back to the surface as rain. Cassini observed clouds forming and dissipating, particularly near Titan's north and south poles. Models suggest that Titan experiences seasonal storms during equinoxes when the sun crosses the moon's equator, triggering convection and rainfall in normally dry equatorial regions. The liquid on Titan's surface collects in lakes and seas, primarily in the polar regions. The northern polar region contains the largest bodies of liquid, including Kraken Mare, which is larger than the Caspian Sea on Earth and is the largest known body of liquid anywhere in the solar system besides Earth's oceans. Ligeia Mare and Punga Mare are also substantial seas. Together, these northern seas and lakes cover an area of approximately 691,000 square kilometers, or about 267,000 square miles. Analysis of radar data suggests these lakes and seas are filled with liquid methane and ethane. The exact composition varies from one body to another, but methane appears to be the dominant component. The lakes sit in topographical depressions, and some show evidence of channels flowing into them, suggesting that they are fed by rainfall and possibly by underground methane aquifers. The discovery of liquid on Titan was confirmed by Cassini in January 2007, when specular reflections, the glint of sunlight off a smooth liquid surface, were observed. The southern hemisphere also has lakes, though fewer and generally smaller than those in the north. This asymmetry is thought to be related to the eccentricity of Saturn's orbit. Because Saturn's orbit is slightly elliptical, the northern summer is longer than the southern summer. This means more methane evaporates from the north and falls as rain, filling the northern lakes. Over the course of a full Saturnian year, about 29 Earth years, liquid is slowly transported from one hemisphere to the other by atmospheric circulation. In addition to the polar lakes, Cassini discovered some small lakes near Titan's equator, which was unexpected given that the equatorial region should be too warm for stable liquid methane. These equatorial lakes may be fed by underground methane aquifers, creating oases in an otherwise dry landscape. The exact mechanism is still being studied, but the presence of these lakes shows that Titan's methane cycle is more complex than simple evaporation and precipitation. The surface of Titan shows a variety of features that indicate active geology. There are impact craters, though fewer than expected for a surface that has been exposed to meteorite impacts for billions of years. The relative scarcity of craters suggests that geological processes have erased older craters over time. Some craters appear to be filled with liquid or with sediment, their rims softened and degraded. Much of Titan's equatorial region is covered by vast dune fields. These dunes are made of small organic particles, complex hydrocarbons that have rained down from the atmosphere over geological time. The dunes are shaped by winds that blow primarily from east to west, creating linear dunes that can stretch for hundreds of kilometers. The dunes are typically about 100 meters high and are spaced about 1 to 2 kilometers apart. Mountains and highlands are also present on Titan. Some of these features rise more than 1,000 meters above the surrounding plains and appear to be made of water ice. The ice on Titan is as hard as rock at the moon's frigid temperatures, so these mountains are essentially made of ice bedrock. How they formed is not entirely clear, but they may be the result of tectonic processes or cryovolcanism. Evidence for cryovolcanism on Titan remains tentative but suggestive. Some features on the surface resemble volcanic calderas, or flow features that could have been created by eruptions of liquid water, ammonia, or methane from the interior. If cryovolcanism does occur on Titan, it would provide a mechanism for replenishing the atmospheric methane and for creating some of the observed geological features. Beneath Titan's icy crust lies another remarkable feature, a subsurface ocean of liquid water. This ocean is thought to be about 35 to 50 miles below the surface, sandwiched between the outer ice shell and a deeper layer of high-pressure ice that overlies a rocky core. The ocean is likely salty, containing dissolved salts and possibly ammonia, which would lower its freezing point and keep it liquid despite the cold temperatures. Evidence for this ocean comes from several sources. Cassini measured tiny variations in Titan's shape as it orbits Saturn, variations caused by tidal forces from Saturn's gravity. The magnitude of these variations, called libration, suggests that Titan's ice shell is decoupled from its rocky interior, floating on a layer of liquid. Additionally, Cassini's gravity measurements during close flybys provided data consistent with a subsurface ocean. The presence of a subsurface ocean makes Titan one of several worlds in the solar system that might harbor environments suitable for life. The ocean contains liquid water, which is essential for life as we know it, and it may have the right chemistry to support microbial life. However, the ocean is buried deep beneath the surface, isolated from sunlight and from the organic chemistry occurring in the atmosphere and on the surface. Whether life could arise in such an environment is unknown, but Titan is considered one of the most promising locations in the solar system for the search for life. On the surface, the methane lakes and seas present another intriguing possibility. While life based on liquid water is what we are familiar with, some scientists have speculated about the possibility of life based on liquid methane or ethane. Such life would have to use very different chemistry than Earth life, but the basic principles, metabolism, reproduction, evolution, could potentially occur in a methane solvent under the right conditions. This remains entirely speculative, but Titan provides a natural laboratory for studying what kinds of chemistry are possible in liquid hydrocarbons. Titan's climate and seasons add another layer of complexity. As Saturn orbits the Sun, Titan experiences seasonal changes that last for years. During northern summer, the North Pole receives more sunlight, warming the atmosphere and increasing evaporation from the northern lakes. Cloud formation increases and rainfall replenishes the lakes. During northern winter, the North Pole is in darkness, temperatures drop, and the lakes may partially freeze or evaporate more slowly. The atmosphere itself shows seasonal variations. During Titan's equinoxes, when the Sun crosses the equator, large storm systems can develop in the equatorial regions, bringing heavy rainfall that carves channels and alters the landscape. These storms are rare but can be intense, producing enough rain to fill lake beds and create temporary rivers. Looking at Titan from Saturn, the Moon would appear as a bright orange orb, larger in Saturn's sky than our Moon appears from Earth. From Titan's surface, Saturn would dominate the sky, appearing about 11 times larger in diameter than the Moon appears from Earth. The view would be spectacular, though muted by the orange haze that fills Titan's atmosphere. Titan represents a kind of analog to early Earth. Earth's early atmosphere, before life produced oxygen, may have been similar to Titan's nitrogen-rich atmosphere with organic haze. The chemistry occurring in Titan's atmosphere, the production of complex organic molecules from simpler precursors, is thought to resemble the chemistry that may have occurred on Earth before life arose. By studying Titan, we learn about processes that may have been important in the origin of life on our own planet. NASA's upcoming Dragonfly mission, scheduled to launch in 2028 and arrive at Titan in 2034, will provide unprecedented opportunities to study this moon. Dragonfly is a rotorcraft, essentially a large drone, that will fly from location to location on Titan's surface, sampling the atmosphere and surface materials and searching for complex organic molecules and potential biosignatures. The mission will explore a variety of terrain types, including an impact crater where liquid water may have been exposed on the surface temporarily. For now, Titan remains a world of mysteries and possibilities. It is a place where methane rains from orange skies, where rivers of liquid hydrocarbons flow through valleys of water ice, where an ocean lies hidden beneath a frozen shell, and where the chemistry of life may be unfolding in ways we have yet to understand. It is a reminder that the universe contains worlds vastly different from Earth, yet governed by the same physical and chemical laws, and that the search for life must consider not just Earth-like conditions, but the full range of environments where chemistry can create complexity. If Titan is Saturn's largest and most Earth-like moon, Enceladus is its most active and perhaps most surprising. This small moon, only about 510 kilometers or 310 miles in diameter, roughly the width of Arizona, has proven to be one of the most geologically active bodies in the solar system. Enceladus erupts geysers of water ice and vapor from its south polar region, creating plumes that shoot hundreds of kilometers into space. These plumes provide a direct window into the moon's subsurface ocean, making Enceladus one of the best places in the solar system to search for life beyond Earth. Enceladus was discovered by William Herschel on August 28, 1789, but for nearly 2 centuries it remained an obscure object, just one of Saturn's many moons. The Oig Voyager spacecraft flew past Enceladus in 1980 and 1981 and returned images showing a bright, reflective surface with a mix of cratered and smooth terrain. The smooth regions suggested that geological activity had resurfaced parts of the moon relatively recently, but the nature of this activity remained unclear. It was the Cassini mission, beginning in 2004, that revealed Enceladus's true character. During early flybys, Cassini's instruments detected something unexpected, a cloud of material surrounding Enceladus. The magnetometer detected a deflection in Saturn's magnetic field, suggesting the presence of an atmosphere or gas cloud. The ultraviolet spectrograph detected water vapor, and when Cassini flew through the region near Enceladus, its dust detector recorded an increase in ice particles. In November 2005, Cassini's cameras captured definitive images of the source: jets of ice particles and water vapor erupting from fractures near Enceladus's south pole. The jets were visible as bright plumes when the moon was backlit by the sun, and they extended hundreds of kilometers above the surface. These geysers, resembling those found in Yellowstone or Iceland on Earth, were continuously erupting, spraying material into space at speeds of about 400 meters per second. The geysers emerge from 4 prominent fractures that cross Enceladus's south polar region. These fractures, informally called tiger stripes, are approximately 135 kilometers or 84 miles long and are warmer than the surrounding surface. Infrared measurements showed temperatures along the tiger stripes reaching as high as 180 to 200 Kelvin, or minus 135 to minus 100 degrees Fahrenheit. While these temperatures are still frigidly cold by Earth standards, they are remarkably warm compared to the surrounding surface, which averages about 75 Kelvin, or minus 324 degrees Fahrenheit. The tiger stripes are complex geological features. They appear to be fractures that penetrate deep into Enceladus's ice shell, possibly reaching all the way to the subsurface ocean. The fractures are approximately 300 meters, or about 1,000 feet deep, and show V-shaped inner walls. They are not static cracks, but are in constant motion, opening and closing slightly, as Enceladus orbits Saturn and experiences tidal stresses from Saturn's gravity. Cassini conducted multiple close flybys of Enceladus, passing through the plumes and directly sampling their composition. The instruments detected water vapor as the primary component, along with carbon dioxide, carbon monoxide, methane, and trace amounts of other organic molecules, including simple hydrocarbons and nitrogen-bearing compounds. The presence of these organic molecules was particularly exciting because organic compounds are the building blocks of life as we know it. Analysis of ice grains collected by Cassini revealed something even more intriguing: the presence of silica nanoparticles. These tiny particles of silicon dioxide can only form under specific conditions. They require liquid water interacting with rock at temperatures above 90 degrees Celsius or about 200 degrees Fahrenheit. This strongly suggests the presence of hydrothermal vents on the floor of Enceladus's subsurface ocean, where hot water from the Moon's interior interacts with the rocky core, creating an environment remarkably similar to hydrothermal vents found on Earth's ocean floors. On Earth, hydrothermal vents are oases of life in the deep ocean. They support ecosystems based not on sunlight, but on chemical energy, with microorganisms feeding on chemicals dissolved in the hot water. The discovery of similar conditions on Enceladus raises the possibility that life could exist in the Moon's subsurface ocean, feeding on chemical energy from hydrothermal activity. The subsurface ocean itself was confirmed through multiple lines of evidence. Cassini's gravity measurements during close flybys detected a mass concentration beneath Enceladus's south polar region consistent with a large body of liquid water. The ocean appears to be about 10 kilometers or 6 miles deep at the South Pole, lying beneath an ice shell about 30 to 40 kilometers or 19 to 25 miles thick. Measurements of Enceladus's slight wobble as it orbits Saturn, its libration, suggest that the ice shell is decoupled from the rocky core, indicating that a global ocean of liquid water exists beneath the entire ice shell, not just at the South Pole. The total amount of water erupting from Enceladus is substantial. Measurements suggest the plumes are ejecting about 79 gallons or 300 liters of water per second. At this rate, you could fill an Olympic-sized swimming pool in just a couple of hours. Much of this material falls back to Enceladus's surface as snow, creating the smooth, fresh ice that makes Enceladus the most reflective body in the solar system. Its surface reflects nearly 100% of the sunlight that hits it, giving Enceladus a dazzling brightness. Some of the material escapes Enceladus's weak gravity. Surface gravity on Enceladus is only about 1% of Earth's, and enters orbit around Saturn, forming the E-ring. This is the outermost of Saturn's major rings, a diffuse ring of tiny ice particles that extends from about 180,000 to nearly 500,000 kilometers from Saturn. Enceladus orbits within the E-ring, continuously replenishing it with material from its geysers. Without this constant supply, the E-ring would dissipate in perhaps 10,000 to 1 million years. Recent observations from the James Webb Space Telescope revealed just how extensive Enceladus's plume can be. Webb detected a water vapor plume extending more than 6,000 miles, or 9,600 kilometers from the Moon, more than 20 times the width of Enceladus itself. This enormous plume creates a toroidal cloud of water vapor in Enceladus's orbit around Saturn, and about 70% of the water spreads throughout the Saturnian system, reaching other moons and even contributing water to Saturn's upper atmosphere. The mechanism that drives the geysers is thought to involve tidal heating. As Enceladus orbits Saturn in a slightly elliptical path, Saturn's gravitational pull varies slightly, sometimes stronger and sometimes weaker. This causes Enceladus's interior to flex and deform, generating heat through friction, much like bending a piece of wire back and forth heats it up. This tidal heating is enhanced because Enceladus is in an orbital resonance with two other moons, Dione and Rhea, which creates regular gravitational perturbations that maintain Enceladus's orbital eccentricity. The tidal stresses also affect the tiger stripe, fractures. As Enceladus moves through its orbit, the fractures experience varying amounts of stress, sometimes being pulled open and sometimes being compressed shut. Observations suggest that the geyser activity varies over the course of Enceladus's orbit, with maximum activity occurring when the fractures are under the most tension and therefore open widest. This correlation between tidal stress and geyser activity provides strong evidence that the geysers are directly connected to the subsurface ocean and are modulated by the opening and closing of pathways through the ice shell. The chemistry of the plume provides clues about conditions in the ocean. The detection of molecular hydrogen in the plume is particularly significant. Hydrogen is produced when water reacts with hot rock in hydrothermal systems, a process called serpentinization. On Earth, this process provides energy for certain microorganisms called methanogens, which use hydrogen and carbon dioxide to produce methane. The presence of molecular hydrogen in Enceladus's plume suggests that similar energy sources could be available for life in the Moon's ocean. Salt was also detected in the ice grains, indicating that the subsurface ocean is salty, probably containing dissolved sodium chloride and other salts. The concentration of salt helps constrain models of the ocean's temperature and composition. The ocean is thought to be slightly alkaline, with a pH similar to that of Earth's oceans, and to contain dissolved minerals leached from the rocky core. Enceladus's surface shows evidence of its geological activity. The South Polar region is covered with relatively smooth, young ice, crisscrossed by the tiger stripe fractures and dotted with small ridges and troughs. The rest of the Moon shows more cratered terrain, indicating an older surface that has not been resurfaced as recently. This dichotomy, a geologically active South Pole and a quieter Northern Hemisphere, is one of the puzzles about Enceladus. It is possible that geological activity has migrated over time, or that the South Pole is currently the focus of activity due to the specific configuration of tidal heating. The temperature distribution on Enceladus is also unusual. Most of the Moon's surface is extremely cold, with temperatures around 75 Kelvin or -324 degrees Fahrenheit. But along the tiger stripes, temperatures reach 180 to 200 Kelvin, and in some spots maybe even warmer. This thermal emission was one of the first clues that something unusual was happening at the South Pole. The amount of heat being radiated from the tiger stripes is far greater than could be explained by sunlight alone, confirming that there is significant internal heating. Cassini observed more than 30 individual geyser jets erupting from the tiger stripes, though the exact number and intensity of jets varied over time. Some jets were large and persistent, while others appeared smaller or only intermittently. The variability of the jets provides information about the structure of the subsurface and the dynamics of how water reaches the surface. Models suggest that the jets may erupt from vertical slots or fissures that connect the ocean to the surface, with the width and depth of these conduits controlling the flow rate and timing of eruptions. The implications of Enceladus's discoveries are profound. Here is a small moon, far from the sun, that maintains a liquid water ocean and active geology through tidal heating. The ocean contains organic molecules, salts, and energy sources that could potentially support life. The geysers provide a way to sample the ocean without having to drill through kilometers of ice. A future mission to Enceladus could fly through the plumes, collect samples, and analyze them for biosignatures, chemical or structural evidence of life. Several mission concepts have been proposed for returning to Enceladus. These include orbiters that would make multiple flybys through the plumes, collecting detailed compositional data. Some concepts involve landers that would touch down on the surface and study the ice directly. The most ambitious concepts envision small probes that could enter the subsurface ocean through cracks in the ice shell, though such a mission would face enormous technical challenges. For now, Enceladus remains one of the most tantalizing targets in the search for life beyond Earth. It is a small moon that defied expectations, revealing itself to be geologically active, chemically complex, and potentially habitable. The geysers that erupt from its south pole are not just beautiful phenomena, but windows into an alien ocean, a hidden world where life might be taking its first steps or might already have flourished for millions or billions of years. And so, the geysers continue to spray water and ice into space, creating the E-ring, feeding Saturn's magnetosphere, and reminding us that even the smallest worlds can hold the greatest mysteries. Enceladus is a testament to the power of exploration and to the endless capacity of the universe to surprise us. We have journeyed through Saturn's realm, moving from the planet itself outward through its rings and moons. We began with Saturn's formation 4.6 billion years ago, when it coalesced from the solar nebula and migrated to its current orbit. We explored its unusual low density, the result of a composition dominated by hydrogen and helium, and we saw how this lightweight structure has shaped the planet's form and behavior. The rings presented themselves in all their complexity, billions of individual ice particles arranged in a structure more than 280,000 kilometers across, yet only about 10 meters thick. We considered their composition, their dynamics, and the ongoing debate about whether they are ancient or young, knowing that, whatever their age, they will not last forever. Saturn's atmosphere revealed its layers: hydrogen and helium clouds, ammonia ice crystals, powerful winds reaching speeds of 1,800 kilometers per hour, and the persistent hexagonal jet stream at the North Pole, a geometric pattern maintained by fluid dynamics and rotation. We traced the subtle seasonal changes driven by Saturn's axial tilt and its 29-year orbit around the Sun. The planet's magnetic field extended our view outward, creating a magnetosphere that traps charged particles from the solar wind and from Saturn's moons, particularly Enceladus. This invisible structure shapes the space around Saturn and connects the planet to its moons through electromagnetic interactions. Time on Saturn operates on multiple scales: the 10-hour rotation that creates a short day, the 29-year orbit that defines a long year, and the billions of years over which the planet has cooled and evolved. These different timescales create a world where rapid atmospheric dynamics coexist with slow geological and orbital processes. Titan emerged as a world of remarkable complexity, with its thick nitrogen atmosphere, its methane lakes and seas, its organic chemistry, and its hidden subsurface ocean. Here is a place that, in some ways, mirrors early Earth, yet operates with different materials at vastly different temperatures. A natural laboratory for studying planetary processes and the chemistry that precedes life. Enceladus surprised us with its geysers, its subsurface ocean, and its potential habitability despite being a small, distant moon. The water erupting from its south pole carries organic molecules and hints of hydrothermal activity, making this tiny world one of the most promising places to search for life beyond Earth. Throughout this exploration, certain themes have recurred. We have seen how gravity shapes worlds, creating spheres, maintaining orbits, generating tidal forces that heat interiors. We have seen how temperature determines what materials can exist in which states: ice on the surface, liquid water or methane in protected environments, gas in atmospheres. We have seen how time allows processes to unfold: rings evolving, atmospheres circulating, moons interacting. Saturn's system is ancient yet dynamic, stable yet constantly changing on various timescales. The planet will continue to orbit the Sun for billions of years, its rings will eventually dissipate, its moons will continue their geological evolution, and the whole system will persist as a testament to the processes that build and shape planetary systems. For us, observing from Earth or sending spacecraft across vast distances, Saturn represents one of the jewels of the solar system. It is accessible enough that we can study it in detail, yet different enough from Earth that it expands our understanding of what planets can be. It reminds us that the universe contains structures of breathtaking beauty and complexity, all arising from the fundamental laws of physics and chemistry operating over cosmic timescales. As you rest tonight, perhaps you can imagine yourself floating in the space near Saturn, moving slowly in the same direction as the planet's orbit. Around you, the rings catch sunlight and scatter it in all directions. Below, Saturn's pale golden clouds turn steadily, the hexagon rotating at the North Pole, storms drifting through the bands. Beyond, Titan glows orange through its hazy atmosphere, while Enceladus gleams white, its geysers shooting water toward the stars. There is no sound in space, only silence. The motions are slow and stately. Time passes in its various rhythms: the 10-hour day, the 16-day orbit of Titan, the 29-year circuit around the Sun. Everything continues as it has for billions of years, governed by gravity and motion, by pressure and temperature, by the simple laws that build complexity from simplicity. And somewhere in that vast system, in Titan's atmosphere or Enceladus's ocean, or in environments we have yet to discover, chemistry may be creating patterns of increasing complexity, molecules organizing and reacting, perhaps even crossing the threshold into what we would recognize as life. Or perhaps not. Either way, Saturn and its moons will continue their ancient dance, illuminated by the distant Sun, slowly radiating away the heat from their formation, existing as they have existed and will exist for billions of years to come. Thank you for joining this quiet exploration of Saturn. If you found this journey through the ringed planet's realm peaceful and informative, please consider liking this video and subscribing to Nebula Nights. There are many more worlds to explore, many more cosmic stories to tell, and many more opportunities to let the universe's calm grandeur accompany you into rest. Until the next journey among the stars, may your nights be peaceful and your curiosity about the cosmos continue to grow.